about waves, and we've been talking about waves in general. And today we're going to focus on sound waves. So if you learned from the Rubens tube, hopefully you learned something from the demonstration. But what I wanted you to get out of it, one of the things, was that sound is a density wave or a compression wave. There are areas where there's high density and low density of the medium through which the sound is traveling. So the propane was the medium. If you have higher density propane, that means it's higher pressure coming out of the hole. That means that the flames are higher. So those areas, the crests of the waves that you saw in the flames, those were the areas of higher density. This is a 6-second long video that just reminds you what the difference is between transverse and longitudinal. Okay, just to give you just a little tiny reminder there.
What are the comments?
Huh?
Not super common.
Okay. Okay. So when we talk about sound, it happens to be something that we use tuning forks a lot for. What is a tuning fork?
Isn't it like tones, right?
Huh?
Does it like make tones?
Yes, it does make tones. Yep, it's something that makes sound. How does it make sound? Okay, you hit it, and if you hit it, it vibrates. Okay, it's got these prongs, and each prong is fixed at one end. And if you hit it, it will vibrate back and forth and back and forth. Okay, usually you hit it with I don't even know where mine is. There's some sort of mallet, but I always use my knee. You can hear it, right? You hear the tone. The lower note is the note that it's supposed to be. If you do this, that's terrible. It's really bad for the tuning forks in density. And it's not the note that you're supposed to be hearing. That high note is just metal, right? This could do it too. Anything that's metal will make the same sound when you hit it like that. But the undertone, the lower note, that's the note that you're supposed to hear. Okay, if it's difficult for you to hear it, you can amplify the sound. On really anything. I can do it on
Cool.
anything that can vibrate can amplify the signal. And if you look at it, you can see it moving. It looks like it's blurry, right? It looks like you can't, your vision is blurred. But it's actually vibrating back and forth. So the way that it makes sound, the way that it turns vibrations into sound looks kind of like this. Okay, if you imagine that the darkness represents density, okay, so the areas where it's moving to the right, this prong is moving to the right, it's squishing the air that's right next to it. And then, as it moves to the left, it creates almost like a vacuum or rarefaction, rarefying the air because there's more space and the same amount of air. Okay, so it creates this sort of I'm squishing, and now I'm unsquishing, squishing, unsquishing, back and forth and back and forth. So that's kind of a slow motion demonstration of that. These come in different notes. This one is 320 hertz. This one is 512 hertz. Anyone know what notes those are?
Off the top of my head.
A and
No and no.
Yeah.
E and C.
So
E and C. And so how can you make a tuning fork the correct frequency?
size.
Yes, exactly, and that's it. That's the only thing, right? So this is one, I made this one, and the only thing I had to do was one tiny calculation to figure out what the wavelength is that I need to make the frequency that I want. And the wavelength directly corresponds to the length of the tuning fork. So this one is 427 hertz, which should be, maybe it's not 427 hertz. That's what I thought it was when I made it. It's probably not. Anyway, this one's 512, this one's 320. And so they make different sounds. This one is a higher pitch. This is, sorry, what?
Isn't the shorter one with the higher pitch?
Yep, so this one makes a higher pitch, and then the longer ones, I think this is the oh, I have 256. So 256 is
Ooh.
And 512, they're both C. How can they both be a C?
Because of the scale.
Okay, what's the word?
Octaves.
They're an octave apart. 256 and 512.
Double 2.
Factor of 2. Yep, double the frequency is an octave. So the next octave up is double the frequency of the one below it. Okay, so anyway, tuning forks they come in handy. Also, they're fun because, sorry. Let me do this without my computer. Because you can do that with them. Which I always enjoy. Okay, so, okay, the Doppler effect is a very important concept. Have you heard of the Doppler effect before?
Yes.
Nope.
Yes.
It's okay if you have not. If you have, so this is a simulation, and what I've done is this is a source of sound, okay? Whether it's a speaker or a person yelling or an ambulance or whatever, it's some source of sound. And when something is a source of sound, when we talk about sound you can't really like direct sound exactly. What I mean by that is, if I'm standing here speaking, he's standing, sound is going out in all directions, right? Yes, there's more sound going this way a little bit, but there's sound going out in all directions. Now, the sound that's going out in all directions, you could draw it like this. There's a bunch of waves, right? And I could draw an infinite number of them. If I were to draw a bunch of waves, they would all be identical, right? Because they're all from the same source at the same instant. And if I were to draw, or I guess trace the location of all of the crests, the first crest that comes out, it would make a circle. Okay, if I were to draw and trace the second crest, it would make a circle. The third crest, it would make a circle. So this is something called a wave front. And what it is, I'll show you what it looks like when it's in motion. It looks like this, okay? It's a representation of the sound waves that are going in all directions. So each one of those red circles represents a crest. And so a crest is moving outward in all directions, okay? And it's called a wave front. And it says Doppler effect for a moving source, and now it's not moving. That's because I gave it a velocity of 0. Okay, this is what a wave front would look like for something that is just sitting there. Okay, but that's also really boring. So let's make our source move a little bit. If we make it move a little bit, as it's moving, it's emitting sound in all directions, but it's moving in one direction. And so as it's emitting the sound, it's squishing it, okay? It's moving and emitting sound at the same time. One way to think about it is if you were, remember in the homework from yesterday, one of the questions was like, you have a baseball pitcher, or was it a tennis ball shooter thing, whatever? If that was moving, okay, if that was moving forward, then the overall velocity of those tennis balls would be larger, and if it was moving backward, the overall velocity would be, the net velocity would be smaller from an observer's perspective. Okay, so it's kind of the same idea. Things, as if you're moving and emitting at the same time, then everything is getting squished together. This is also true for light. Light does the same thing. Light changes color if the source is moving. So if we have a source that's moving away from us, everything looks a little bit, you can't really see it with your eye, but everything, the wavelength shifts to a redder color. And if it's moving toward you, the wavelength shifts to a bluer color. And that's actually, that principle is how we discovered that the universe is expanding and accelerating, because we look at things that are farther away, and they're moving away from us faster than things that are closer. Anyway, so let's make this a little more exaggerated. So now let's say that the speed of our wave is, speed of the source is a lot faster. Now you can see the effect a lot more. Okay? Now imagine that you're an observer or a listener, okay? It's sort of, it's hard for you to imagine unless you have an example. So the traditional example is like a siren, right? You have an ambulance or something driving by, and it's emitting a sound. It's pretty constant, and as it drives by you, you can hear the change in pitch. Yes. If this is an ambulance and you're on the right-hand side, it's moving towards you. Do you hear a higher pitch or a lower pitch than the ambulance would normally emit?
Higher pitch.
A higher pitch, and how do you know that? Higher frequency. So frequency and pitch are directly related to one another. So a higher frequency is a higher pitch. If you're behind the ambulance or the source, then it's a lower pitch. What if you are in the source?
You don't hear it.
You hear the same.
Yeah, you hear the exact emitted frequency. You don't hear any shift at all. Okay, well this part is not that exciting, but what if instead of going, these are arbitrary units, notice they say units are arbitrary, so the speed of the wave is 80, okay, whatever that means. And let's say, what if the speed of our source was also 80? Whoa. What will happen? Guesses? Guesses?
It's gonna be like, the sound's not gonna ever be in front of the source.
Okay.
It's gonna be on the crest like first. I don't know. Let's see.
It's definitely hard to explain. You might have like, you're saying the same, I don't know what that means, but I'm sure you have a picture in your mind of what that means. Does it mean that?
Yeah.
Okay. Okay. So what that means to me is, like you were saying, it's never going to be in front, the sound will never be in front of it, the sound will always be like on it, right, if it's traveling at the exact speed. So most things don't travel at exactly the same speed as sound, right? You have to speed up to that point, and then usually you don't just say, oh, I'm at the speed of sound, I'm just going to stay right here. The point is usually to break the sound barrier, right, to break the sound barrier. So this is an example of something that is traveling at the speed of sound. Notice that with these wave fronts, they represent crests, okay? Crests, if we were talking about sound waves, are areas of high density, okay? Areas of high density are all lined up on top of each other. That makes areas of really, 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 really high density, right? Remember the whole superposition or adding up the waves together? If you've got a crest and another 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 crest, you just keep adding them up until you have like a giant, super, super dense region, which actually I will find in 1 second.
What is that?
Looks like, hold on, not that one, not that one, not that one. Okay, hold on, I will relate to it. You can see the air as it's squished together in that shape. So what you're viewing there is all of those wave fronts on top of each other, and they're creating areas of such high density that you can see it. So let's talk about this concept of resonance for a second. Resonance is probably the most important concept that you're going to learn when we talk about sound, and it's also the weirdest. And so resonance is this idea, have you heard the term before?
Yeah.
If something resonates with you, what does that mean?
Bounces around inside you.
Okay, that's a little literal, but yeah, I mean, so the idea is if like, oh, that really resonates with me, that means like that particular concept or thing that someone said meant something to you in particular, and you liked it a lot or whatever. And so that's how I like to think about resonance. Everything has a particular frequency with which it likes to vibrate. Okay, so for example, this tuning fork has a resonant frequency, and it's 320 hertz. When something has a resonant frequency, if you reach that resonant frequency, the amplitude of vibrations all of a sudden like completely increases. Okay, and that's very well seen with this demonstration, which is these wine glasses that are filled with water. You don't need water, right? This one's empty. I don't need water. If I want to resonate this wine glass with a particular frequency, I can just
Crystal.
okay. So the resonant frequency the wine glass is whatever it was able to vibrate at with a higher with a higher amplitude. Sorry. This one has a different resonant frequency because it has a different mass and a different shape. And this one has somewhere in between. Okay, it vibrates with enough amplitude to create enough sound that you can hear it pretty loudly. If I wanted to really resonate this, I would take that note and I would amplify it a lot. And then what would happen?
Break.
This thing would break, right? Because if you take glass and you make it move with a high amplitude, it doesn't restore back to its original shape at some point, right? And that's when it breaks. And there's a video of that.
What is the amplitude mean exactly?
Amplitude is like how much it displaces from its, like the amplitude of that, if you look at it before it breaks, you see how much it's moving from its original position. That's the amplitude.
So it's at the medium?
Yep.
You said.
Okay, so
Barbie doll with a hot rod. So it's
24 hertz sine wave and a 24 frame per second camera.
What just happened?
Magic. Just kidding, it's not at all magic.
Sure?
Positive.
That's actually so sick.
so bad.
Yeah, wait, is that a spiral?
It looks like it.
Oh my god. Oh my god. That is so cool. How is that possible?
How is it possible? Let's take a step back for a second. Let's say that you have a clock, okay? And your clock only has a second hand. And so here's your second hand, right? It's starting at 0. And you take a picture, okay? Let's say the next time you take a picture is 1 minute later. And then the next time you take another picture is 1 minute later. And then 1 minute later. And then 1 minute later. If you put all those pictures together, what does it look like the second hand is doing? Staying in the same place, even though it's not. Right? That wave is propagating the water forward. The entire wave is moving. But if you take a picture each time that a crest is in the same spot that the one previous was, it's going to look like it's not moving. Right? So if we have, so let's say we have, our wave starts and it looks like this. And we take a picture. And then that wave has moved on and that one's over here, but then there's another one exactly in the same spot. And because the frequency of the wave is 24 hertz and the frame rate of the camera is 24 frames per second or 24 hertz, it takes a picture of the wave each one wave. Okay? So here's a question for you. What if instead of taking a picture of my second hand every minute, I took a picture every minute and 1 second? It would slowly look like it's moving forward, right?
So to the guy who's actually there, it looks like it's just like shaking back and forth, but to us,
It's just because of the camera. Okay, what if instead you took a picture every 59 seconds? What would it look like it's doing? Going backwards. So that's what they're going to show you next. They're going to have, instead of 24 hertz, they're going to go 25 hertz.
so is that supposed to be a wave or a spiral?
It's probably it's a spiral, I guess, but it's in the shape of a wave. I think it was just accidentally a spiral. So this is the forward effect, which was a slightly higher frequency.
It's like Rizzy.
Okay, now that it's slightly lower frequency.
What?
That's so cool.
What?
This is the same idea. I showed you this before, but now you can understand it a little bit better. This is a camera on a helicopter rotor. And at some point, the frame rate of the camera, imagine that instead of a helicopter rotor, it's a second hand. It takes a picture once every time it goes around.
Sound is a wave that we perceive with our ears. It makes our favorite music and it keeps us out of danger, but it's so much more than that. Hey everybody, thanks for checking out D-News today. I'm Trace. Now listen up. Sound is extremely powerful. It's made of invisible waves of energy passing through substances, ground, water, air, particle to particle. The human ear can perceive these waves as long as their frequency is between 20 hertz and 20,000 hertz. Anything above or below that we can't hear, but they're still there, because these waves contain energy. And with enough din, you can make these waves do some incredible things. Outside of medical technology like ultrasound, one of the most commonly known ways to make sound do something is by breaking a glass. This works only when the sound wave is at the exact same frequency as the object you're shooting at. If you gently flick a wine glass with your fingernail, you will hear its frequency. Match that tone and turn the volume up, way up to like 11, and that glass will probably break. Also within the range of hearing is sound levitation. This is way cooler than breaking stuff, if you ask me. Sound levitation has been around for years, but until recently, we couldn't do much with the stuff once it was levitated. It just sort of hung there in the air. Thanks to advances at a Swiss university called ETH Zurich, we can not only levitate stuff, but we can move it around, adjusting floating fluids. This works by using the energy in the sound waves. In this apparatus, the energy waves reflect back and forth so quickly they form what's called a standing wave, or a specific point where the energy from the sound can hold an object in midair. Think of it like these silly executive desk toys. The ball in the middle, that's the standing wave. The thing that they just figured out is how to move the stuff once it's levitated. Now they can use this system to manipulate liquids, combining and separating them, all without touching them with human hands, which is immediately applicable to drug manufacturing. That's kind of cool. These energy waves can do a lot of other stuff too. The LRAD, or long-range acoustical device, is a weapon that shoots sound. It's like a sonic death ray, without this death part. It can produce so much sound that you feel physical pain, like 160 decibels. That's loud. Think NASA rocket launch. But it won't kill you. You just really hurt, like a sonic hurt ray. If you combine some of those technologies, sound can produce really strange effects. In the 1950s, NASA and the US Navy built a device that produces ultra-low frequencies, or ultrasonic sound. If you pointed it at a person and set it to 19 hertz, people would have vision problems and get spots and stuff, because 19 hertz is the resonant frequency of the human eyeball. Kind of like that wine glass example we talked about. If you turn the volume up, people actually would have trouble breathing because the low frequencies were impacting the lungs like energy waves, and if you shot it through the ground, your skeleton would vibrate, causing nausea and joint pain. So which of these sound inventions is your favorite? The levitating one?
So the idea of resonance becomes clearer when you think about the eyeball thing, right? There's a particular frequency. Your eyeball will vibrate with any frequency that you choose to vibrate it. But if you choose the right one, the amplitude of vibration will increase, and then your eyeball will explode. Okay, let's talk about standing waves. Standing waves are a very, 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 very important concept that I want you to know. So here's the idea. We talked yesterday about waves interfering with each other. And when you have two crests and they're on top of each other, they make a bigger crest, right? If you have a crest and a trough, then it makes a flat line, right? This is called constructive interference and this is called destructive interference. And it depends upon a lot of things, right? But a standing wave is a special kind of interfering pattern, and it is a wave and its own reflection interfering with each other. Okay, so it's a wave that's going in one direction, let's say to the right. Let's get this party started here. To the right, there it is, it's the red one. Okay, and then it's going to reflect, and when it reflects, it's going to invert itself. Okay, so the reflected wave will be going in the opposite direction to the left, and it will also be going below the axis first instead of above the axis first. So just watch.
It's like once it hits the object.
Yep. And so now here's the reflected wave. Okay, so the reflected wave is passing through the original wave as the original wave continues to the right. So it's a continuous wave, it's not a single pulse. To the right, and it's experiencing some sort of interaction with the wave that's moving to the left. Okay, they're interfering with each other. What I have taken off, what I unchecked here, was the resulting wave. Right? These are two individual waves, and what I want to show you is what the sum of those waves looks like. So the red one is definitely moving to the right, and the blue one is definitely moving to the left. Here's the resulting wave. The resulting wave is definitely not moving right or left, hence standing. And only particular waves can become standing waves on a certain medium or in a certain situation. So to create a standing wave, you have to have the right circumstances.
So what does the wave reflect off of?
It doesn't have to be an actual like object necessarily. For example, if you have a guitar string, okay, a guitar string is fixed at both ends. If I wanted to create a standing wave on this guitar string, there are certain things that have to be true. It's got to stay fixed at both ends, otherwise it's not a guitar string, right? It's something else flying through the air. So it's definitely fixed at both ends. There are only certain parts, like a standing wave has two really important parts to it. One of those two really important parts are these points here, where there is never any motion. Okay, and those points have to correspond to these points. And so depending upon the length of the string, only certain waves or wavelengths can fit on that string. That's why guitars play different guitar strings play different notes when you hold down different locations. You're essentially changing the length of the string. So it's not necessarily reflecting off of anything except the fact that it's fixed in one point. Same thing in a tube, like that tube. To create a standing wave in the Rubens tube, it has to fulfill certain conditions. There has to be zero net motion at either end of the tube. To create these places where you have zero motion, and then the places where you have maximum displacement in either direction. Okay, and those have special names. The place with zero motion is called a node, and the maximum displacement is called an antinode. Okay, and so I can create a standing wave on a slinky. Who's my slinky helper? John? Okay. So just to show you the reflection, if I just send a single pulse down, watch how it reflects off of the fixed point down there. It changed direction, right? And so if I sent another, then it would interfere with the one that's going in the opposite direction. But if I want to create a standing wave, there are only a certain number of waves that I can create that would fit on this thing. And so I'm going to try to create a standing wave. There we go. So you can see, kind of, it's hard to do this particular one, but there's a point in the middle that's sort of not moving very much, right? And then you can see these points here are moving a lot. If I make a different standing wave, you can see that there are points in between these crests that are, sorry, that's not a very good standing wave, it's kind of moving. Let me try to make a different frequency. There we go. You can see that there are, sorry.
You're trying.
It's hard because you want it to look like it's not moving down. There you go. Something like this. You can see that there are parts that are not moving very much, and there are parts that are moving a lot. Anyway, sorry for this. So that's and standing waves are, the concept of a standing wave is the general governing principle behind most musical production. All stringed instruments are governed by the fact that they have to create a standing wave, as are wind instruments. If I have a wind instrument, like a straw, or an oboe,
Oboe.
then I can make a sound, but I can only make basically one sound, because only one wavelength will fit in this cavity. Okay, other ones will, but I can only play the easiest one, okay, that will fit into the length of this tube. And I also can't look at you like that.
Oh, yeah.
Are you rolling both your lips and like? Are you rolling
Don't
both
put
your lips?
chapstick on before you do this, huh? I'm sorry, what?
Did you roll both your lips in?
Yeah.
Oh, I remember.
Okay, so that's, if I want to change the note that I'm playing, in the same way that if I wanted to change on a guitar string the note that I'm playing, I would just change the length of the string, now it's a different note. You can change the length of your instrument.
Yay!
Let's do this so close.
Something died.
So, the way that, you don't do that with your musical instruments because you can't like cut a musical instrument and then put it back together, right?
So you
But
press down the hole.
exactly, so you can change the length of an instrument by also uncovering or covering areas that create, that change the circumstances of the standing wave that is created inside.
Everyone else have to play with
Um,
You're like,
Huh?
I'm pretty sure every kid like fifth grade play this like
Yeah.
It was, I remember it was 4th grade for me.
I got
back in the
I
day.
got up to my black belts and I got teacher belts.
Whoa!
Yes.
I will never play this one because there have been some number of mouths on this that I don't know how many, but it's
You
more
just put
than
the dishwasher.
I ever want to.
I wash my dishes.